In the most recent update of Stationeers, we got a new form of IC logic with the logic sorter and printers, which are currently in the beta as I'm making this video. Rather than using the stack from an IC, you can now manipulate a stack inside of certain machines themselves to do various things, freeing up valuable processing power to the IC itself. And in this video, I'm going to cover all the possibilities we currently have with these features. I also want to preface the video by saying I'm not a computer science person, nor a programmer, so my terminology will probably be wrong. Furthermore, I do not expect you to know binary, nor will I be teaching it. I will only cover relevant parts that teach you what you need to know to apply to Stationeers. Timestamps will also be available in the description if you think you feel comfortable skipping to any part of the video. Without further ado, let's get started. Firstly, we need to understand what instructions are. An instruction is just a number that contains information on how to do something. The first part of an instruction, an opcode, tells you what the machine should do with that information you give it. Now, don't get intimidated that I'm showing you binary. The actual values here don't matter. I'm just trying to show you the concept of components to those instructions, which are separated by the yellow pipes, and that these instructions expect different components. For example, our first instruction just has an opcode first and then some kind of hash we give it later, whereas the second one expects a quantity after the opcode, before the hash. It's important to note that this order does matter, and that's what I'm trying to highlight here. So don't put the wrong information at the wrong part of the instruction, or it will not work correctly. So how do we put information into these instructions? You need to learn basic bit shifting. Don't worry though, the second one is going to teach you the very basics of it. But first, let's highlight an example of why you need to learn bit shifting. I told you the order that we put the information in does matter. So let's try running this code where we put the hash of iron ingots, which we'll pretend is a number 15 for simplicity's sake. We'll put this value into an instruction without bit shifting. Setting R0 to the hash and looking at the binary representation, we can see here the number 15 gets put where we want to store the opcode. So how do we fix this? With bit shifting. Bit shifting is just the process of shifting that number a couple of bits to the left or right. We can shift to the left using SLL, which stands for shift logically left. Our code here says shift the hash 8 bits to the left and fill the vacant bits on the right with 0, and then store that result in R0, which in this case is alias to the word instruction. Looking at the first binary number, we can see that the 4 ones are now correctly shifted left of the yellow pipe, starting where we expect our prefab hash to be. So how do we put the correct opcode in after this? Well, let's say the opcode we want to put in is just the number 1. We can just use an OR operation. OR takes 2 inputs. If either of those inputs is a 1, then the resulting bit is a 1. Otherwise, it's 0. And congrats, you now have a ready instruction. But before we put that instruction to our logic sorter, we need to address an elephant in the room that may cause you headaches on your new coding adventures. And that is the difference between shifting logically or arithmetically. There are special rules on how computers represent binary numbers, especially negative numbers. I'm not going to address them in this video, but the important takeaway, especially writing instructions with hashes, is that those hashes can sometimes be negative, which you can always check in the Stationpedia. Generally, you are going to use SLL most of the time, but on the off chance you need to use SLA, which replaces the vacant bits not with 0, but rather whatever the leftmost bit is. Things could end up as not what you expect. In this just arbitrary example, we can see we have the 3 leftmost bits as all 1. If we do that standard 8-bit left shift using either SLL or SLA, we get different results. Here we can see SLL behaves as normal, whereas SLA puts a bunch of 1s where we expect to put the opcode later, pretty much ruining our instruction, because the leftmost bit is a 1. Most of this is more relevant when we talk about using the internal stack in the printers, which will be in the next video. But keep the concept in mind and generally use SLL. So back to that instruction I had you OR together. What is it? Well, you actually just wrote an instruction that will filter only iron ingots. In the Stationpedia, under the logic sorter, we can see what those opcodes do. And in this case, the opcode 1 I gave you says filter something when the prefab hash is equal to the prefab hash given. So how do we put this instruction into the sorter? Well, I've said it twice now. We use put. The last instruction in this code says put the instruction in the sorter at address 0 of the stack. Let's also cover opcode 2, which is very similar to 1 but does the opposite. It will only filter things that are not iron ingots, since the opcode is called not equals. Let's keep going exploring the other instructions, and here things get a little more complicated but also more powerful. Looking at opcode 3, we can see different kinds of comparisons based on the sorting class. What is a sorting class, you might ask? Well, it's just a different way to group different types of items. What you can do to see them all is open up a computer or laptop in-game, click the X in the top right, and type sorting class, and it will tell you what the different ones are. In this example, we are going to write an instruction to filter all ors. So let's work line by line on this code after the aliases and the defines. Our first SLL shifts the sorting class for ors 16 bits to the right. Why 16 and not 8, you might ask? Well, look at the instruction in the top left. The first 8 bits are opcode as usual, but the second part is a different component. So we need to shift another 8 bits to the left for a total of 16 bits. Also, why am I creating my instruction from left to right? Well, it's just how I like to do it, and it helps me visualize the OR operations in my head. You can do it however you want, but just make sure you are shifting correctly. So moving on to the next component, which is a condition. We again need to shift 8 bits because we need to maintain that empty space for opcode. And this time we fill it in with the constant equals. Since in this example, we want to filter if input is equal to an OR. Now let's OR everything together. First we OR the sorting class in the condition, and then the result of that, we OR with the opcode we want to put in, giving us our total instruction. And then we put that into the sorter. Now here's that same instructions, slightly more, powerful, you could say, little brother. This one does the same thing, but uses a slot class, which is different from a sorting class. And again, you can find that by going into a computer or laptop, clicking the X, and typing in slot class. I'd recommend you try writing your own code based on the one I have here, but make it filter any ingots. Up to this point, you've probably been wondering, I can do all this all with just a setup, filter, and a motherboard. Why should I use this IC variant? A great question. That has 2 answers. Firstly, it's cooler and makes you feel smart. Secondly, I haven't touched any address other than 0 on the device stack in my code. What do I mean by that? I mean you can compound instructions. Let's say you wanted to filter only stacks greater than 100 of something. Well, this next opcode allows you to filter based on quantities, so you can do that. Here I again start by my leftmost instruction and shifting 16 bits to the left before I put in my quantity, which is defined as above as 100. Then doing the same thing in another register, I shift in the greater constant 8 bits to the left rather than 16, since again, we need to leave space for that opcode. Finally, we just OR everything together and put it in address 1. Why did I do address 1? And what's with the weird first instruction in address 0, you might be asking? Well, the final opcode is a little different. It is an instruction for other instructions. In this case, this one means whatever the next instruction is, only do it X amount of times. Note that since this instruction needs another instruction to be useful, it must be in the address before the instruction you want it to apply to. Finally, since we can compound instructions, it's important to remember that the logic sorter has 3 modes to it. By default, it's all, which means all instructions must be true for the item to filter. You can also set it to work in a way such that any instruction you put in is true, so not all of them, just one of them has to be true. And finally, you can set it to none, which means that none of the instructions have to be true for the item to filter. Pretty much the inverse of all. And maybe you're not sold yet, or still a little confused. Let's jump to the game and do some examples together. So let's say you just got back from a mining trip and you want to deposit all your ores to an ore management system and your other things somewhere else. Here the sorter will send our ores to the ore silo side and the rest to the vending machine side. I also have this backpack full of various items for us to deposit. The first thing we are going to do is alias our sorter, which is on pin D0, just so it's more readable. Next, let's have a look at our instruction. In this case, we will use FilterSortingClassCompare, which we can see takes 3 arguments: the sorting class, the condition, and the opcode. To find the sorting classes, we need to go click the constant section in a computer and type in the sorting class. And scrolling down, we can see the sorting class for ores. So the first major instruction we're going to do is shift in that sorting class for ores 16 bits to the right. Notice that I'm doing this differently than I did in my presentation. This is because in that time I found out there's a bug where if we define a sorting class constant, or any constant I'm pretty sure, and then try using that, class is actually not a number here. So the code will not work. This might be fixed by the time you're watching this video, so give it a try. If it doesn't work, do it this other way I'm showing you here. Next, we're going to put in our condition, which in this case will be equals, since we want if the input is equal to an OR, send it to the OR side. And remember, since that is 8 bits, we're only going to shift by 8 rather than 16. Finally, it's just a matter of ORing everything together. In this case, I'm dumping everything back into register 0. You can do whatever you want. I'm just doing what's simple for me. And finally, don't forget to OR that opcode in, which you can click in the Stationpedia to copy to your clipboard and just paste it in like that. Finally, we put the instruction into the device at address 0. Since we're not doing multiple instructions or a limit, we can just put in the first one. So the code is complete, and let's drop this backpack in and see what it does. And we can see the items going to the left that are not ores to the vending machine, and the ones that are being filtered are all ores. So the code is working perfectly. So for this next example, let's say I only wanted to put stacks of 25 ore into the silo. How do I split them? Well, there's another instruction I can use to send them back to the stacker here, which is set to 25. And if the stack is 25 or less, then it will get put up into the silo. So again, the first thing we're going to do is alias our sorter, just so it's more readable. It's good practice to get into that. Let's have a look at the instruction we're going to be using here. In this case, it's FilterQuantityCompare, since we want to check the quantity and make sure it's 25. Here we can actually use define, since I'm not defining a constant, I'm just defining a random number. And I want to say if the amount of ore is greater than 25, put it back to the stacker, otherwise put it in the silo. So again, the first instruction we're going to do is put in that quantity, 16 bits to the left, because that is what it says here in the Stationpedia. Next, in a different register, we're going to put our operation in, which in this case is greater than, because if it's greater than, we want it to filter and put it back to the stacker. And that's only 8 bits this time. Finally, just like the last example, we're going to OR everything together and use our correct condition, our opcode, and put that into the stacker. Or not the stacker, the sorter. And let's load up this backpack full of stuff in the onloader again and watch it all go through. We can see here that the ores immediately get dumped back to the stacker because they're all in stacks of 50, and once that's complete, they're being allowed into the silo. Which in this case, I actually forgot to wire it up, so it's not actually going to accept anything. So to show you that it worked, I'm going to break apart the chute here and try to grab one of the stacks. And everything goes flying. And you can see the copper here is a stack of 25. We grab something else, it's also going to be a stack of 25. And that's all the examples I'm going to cover in this video. So if you guys want to see me cover the printers next, then feel free to like and let me know.